Welcome to the 2020 home edition of the Collaborative and Interoperability Congress, presented once again by Action Engineering. The subject of this week's virtual event will be model-based technical data in the Department of Defense. We will be discussing the DoD Engineering Data and Modeling Working Group, the importance of an enterprise-wide MBE policy, rights in technical data, and respecting intellectual property. Hi, I am Ben Castle, a senior consultant at LMI specializing in technologies related to the digital thread-enabled model-based environment. You may know me from such epic events as the NIST-sponsored Model-Based Enterprise Summit, the Defense Manufacturing Conference, the National Shipbuilding Research Program, and of course, past face-to-face collaboration and interoperability congresses. Over the past 5 decades, I have been dedicated to the evolution from a paper-based to a 3D model-based environment for technical data within the U.S. Navy, which I suppose qualifies me to be a former insider. But this is more than just CAD. It is about domain-specific data definition with an emphasis on the semantic definition. With my good friend Paul Wong from the Office of Naval Research, the DoD Engineering Data and Modeling Working Group was established and continues to be an advocate to not only establish but to carry out policies that will enable the availability and flow of 3D model-based technical data in all phases of a product's life cycle. Do I really need to tell you who needs a model-based definition? Why models are better than drawings? And how, without models, the really cool technologies that will enable a digital engineering ecosystem simply will not work? Probably not, because 95% of the people in this room have observed firsthand the power of the model-based definition. I'm going to guess that not only are you an advocate for the model-based definition, but for a generative, semantic model-based definition that enables hands-free machine-to-machine communication both within and across enterprise boundaries. Sorry to disappoint you, but this talk is going to be mostly about policy and vision and very little to do with the tools and building models. So, we know that the model-based definition provides the foundation for the MBE, but what is an MBE? Turns out MBE is not so simple to define because there are at least 3 E's in MBE. E is for engineering, performing engineering tasks using 3D model-based product and other technical data in lieu of extracting information from documents. E is for environment, leveraging the digital thread to integrate between data repositories and applications, in which you can determine the pedigree of the data and identify the source of truth, that you can generate derivative data to meet a specific need, that you can augment derivative data and the source of truth with additional data, thus increasing the scope of authoritative data. E is for enterprise. All of the information typically found in an entire set of engineering drawings and associated lists. Traditionally, this includes shape definition, product manufacturing information, materials, and assembly fit-up. This must expand between the domain of design and manufacturing. It is, in effect, the technical DNA of your organization. Most of us in this room would be content to concentrate on building models that can be used to define what it is we want to create. Design tools, engineering analysis, a little simulation, and a whole lot of manufacturing. Dealing with that nasty world of taxonomy and ontology is a necessary evil, but at least we are still dealing with creating things. But having to venture out into those last 2 E's, enterprise and environment, is something we might be able to live without. But if we don't do it, who will? And even when we do become involved, our experience has been less than positive. We are the dwellers of the basement of the science building. We are begging for products that most program managers do not want to buy, most suppliers do not want to sell, and the problem is exacerbated because the very last thing that our software providers want us to have are tools that will enable us to integrate our technical data across competitive offerings. The sad truth is, we need to advocate for the acquisition of product model data. We need to advocate for top-level policy and to have that policy enforced. And we need to advocate for data standards. Ideally, the policy developed at the executive level will have considered and will enable best practices the users have bought into for creating and maintaining the 3D model-based definition. Executive level policy will provide the environment that will allow the workforce to have the tools, data, and knowledge necessary to perform at the highest level. But this is not just a pleasant coincidence. It occurs because the subject matter experts are not only involved in the formation of policy, but assertively represent the technical workforce within the business context of the enterprise. The policy will enable enterprise readiness, recognize the boundaries of the intellectual property that will be obtained from industry, while aggressively protecting the government's rights and technical data, ensure availability whether it is created organically or acquired from an OEM, especially that product data that defines form, fit, function, and is necessary for operations, maintenance, installation, and training. But our executives are not equipped to develop this policy. It is our duty to make sure the policy will be effective, is sensitive to the state of the art and emerging technologies, embraces the state of industry, provides the flexibility to integrate those newer technologies, and provides a balance between authoring and archiving of technical data. Subject matter involvement in policy development is nothing new. A recognition for the need to advocate for technical data and a model-based definition had been known for years, but really came to the forefront in 2009 when a group of 77 subject matter experts gathered at NIST in Gaithersburg, Maryland, to discuss and commiserate about technical data package requirements for manufactured parts. I guess we could say it all started with the discovery of descriptive geometry in the 18th century, but remained relatively unchanged for about 200 years until the advent of solid modeling. During the first decade of the 21st century, there were two significant events that pointed us to where we are today: the NIST Technical Data Package Workshop and the formation of the DoD Engineering Drawing and Modeling Working Group. Subsequent events included the expansion of mainstream STEP to include PMI with the release of AP 242 and the release of MIL Standard 31000. But the new STEP AP was not being implemented as rapidly as hoped and needed. And MIL Standard 31000 was drawings first, model a distant second. In 2017, it was recognized that if you want a model-based enterprise, you need to have a model-based definition. In recognition of that, the DEDMIG was renamed to emphasize data and is now known as the DoD Engineering Data and Modeling Working Group. Oh, by the way, the membership is open to all, and it don't cost nothing, and you get a really cool membership card. But what is DEDMIG, really? Originally, it was the group that was frustrated with the lack of good technical specifications to obtain shape data for 3D mechanical parts suitable for manufacturing and inspection. This group, mostly Army and NIST, were frustrated with being lumped in with drawings and associated lists. Although models had made it to the data item description, you could tell it was an afterthought and still being treated as such. The data item description referenced standards that cared more about center lines and object lines than about geometry. This did make sense, though. After all, the vast majority of the industry relied on that information to convey information about the part. Yes, kids, in the old days, the thickness of a line and its font on a drawing conveyed as much knowledge about that part as does the feature control symbol today. The specification even provided guidance on the legibility and size of text. Enough of that. It was time to specify the requirements and advocate for the acquisition of product model data and to move on from drawings. It was the Joint Defense Mantech Program Advanced Manufacturing Enterprise Subpanel that would lead the charge. The charter was developed by the subpanel and signed by Adele Ratcliffe, the Mantech Program Manager. And DEDMIG, the newly formed ASME-MBE Standards Committee, the NIST MBE Summit, and the major reason why we need the Collaboration and Interoperability Congress is because we need a robust and consensus approach to creating, managing, and archiving that information so necessary to support machine-to-machine communications. We have no choice but to change our emphasis from a document-centric mentality to a minimally annotated, model-based definition that directly enables machine-to-machine communications. But in order to make this work, we cannot forget that humans will need to be able to extract information from these models and that we will require applications that can generate a human-interpretable presentation on demand in near real time. We also need to be met halfway, which will require a willingness for those that are not living with us in the basement of the science building to accept education to prepare for this digitalized technical data. And it won't take long to see how much more you can get from this more complete set of technical data. By simply expanding the use of ASME Y14.5, a significant level of design intent can be communicated. This primary surface needs to be flat so it will not wobble. The bolt hole needs to be perpendicular to the mount so it will sit flat. And the location of the ball mount needs to be in alignment with the mount and the trailer. All of this can be extracted from the semantic definition in an easily communicated, standardized graphical presentation. With the semantic definition, it will no longer be necessary to draft a presentation view. No longer will it be necessary to specifically place and orient basic dimensions. And bonus, we have all the information necessary to support machine-dependent processes from shape definition to analysis to inspection. But wait, this begs a bigger question which maybe we can address at the face-to-face. Why do we need so many standards that can convey shape, features, PMI, and other product data, including visualization data? I guess, pun intended, it all started with the initial graphics exchange specification. Okay, most of you know it as IGES, but what you may not know is you could tell who was in the inner sanctum because they would pronounce it, I guess. I wonder if there is anyone in the room today that does not know what IGES is. What you may not know is that IGES is much more than drawings and more than wireframe. It can handle constructive solid geometry, as well as non-uniform rational B-spline-based boundary representation models. And it allows not only for a robust set of non-graphical attributes, but for a user-defined attribute as well. Sorry about the diversion, but as you can tell, I'm an IGES guy. There, I said it loud and proud. IGES even had a piping application subset, and there was a weld path and cross-section subset in the planning phase. The Seawolf submarine program in the 1980s defined a structural steel IGES subset to exchange plates, stiffeners, beams, and other parts between Newport News and Electric Boat. IGES was okay, but as with all neutral file formats, was struggling, compounded by relative low-performing hardware and inefficient programming environments. It was difficult to implement data exchange, but IGES was a great start. But alas, even I can recognize when it may be time to retire that comfortable old recliner. Championed by NIST, a better way was proposed that included the adoption of a formal modeling language and an emphasis on the definition of products. IGES was based on the definition and exchange of entities. STEP was based on the definition and exchange of objects. There was a planned transition. STEP had to include all of the functionality of IGES, so it was not much of a surprise that the early adoption focused on the definition of surface and solid model geometry. Unfortunately, the promise and power of STEP never fully materialized, and it has not progressed much further than IGES. Almost 40 years after STEP replaced IGES as the predominant neutral file standard for geometry, there still is not widespread use of a feature model. Why is it important to spend so much time discussing this transition from IGES to STEP? Because this is the major symptom caused by not having a robust and enforced model-based definition policy. Around 10 years ago, there became a lot of interest in model-based definition. Sketch-based feature modeling systems were quite popular, and with ready access to finite element tools on the desktop and even manufacturing software, there was a lot of interest in integrating the computer-aided design data with engineering data and manufacturing data. There was a lot of interest within the Advanced Manufacturing Enterprise subpanel across services. The focus of the mainstream CAD vendors were on surface and solid geometry. It is not surprising that the domain of Step Translator in those early days were identical to IGES. Around this time, support of IGES was waning, and although it remained quite popular, the majority of CAD vendor resources were being dedicated to step geometry. And although the vision of STEP was the exchange of product model data, this clearly was not the case, with one notable exception. The marine industry, which invested tens of millions of dollars to define application protocols for ship structure, piping, arrangement, and molded forms. But the focus on geometry by the mainstream CAD vendors has continued for the last decade. With the planning and subsequent release of AP 242, this focus has expanded to include product manufacturing information. But the emphasis is still on the geometry that makes up the shapes of the parts that are being manufactured. But something interesting is happening. Other standards are developing as well, primarily lightweight representations for visualization and internet presentation. And then PDF publishes a precise version, the emphasis being on technical publications that contain graphics. But then JT shows up, and it also has a lightweight representation and an exact representation. QIF contains geometry definition and features in which the scope appears to heavily overlap STEP. Now we have several different standards in which we have major overlap. An argument can be presented that we have in fact reduced standardization through the release of standards. But maybe this is not such a bad thing. As long as the standards can be mapped and the IT industry continues to provide tools that can rapidly develop applications, how about we let the market rule and see what happens? So we all agree that the model-based definition is necessary if we are going to design, engineer, and build products using currently accepted practices. Computer-aided design for 3D shape, finite element analysis to calculate engineering properties and simulate the product under various conditions, computational fluid dynamics, discrete event simulation, and the up-and-coming integrated computational materials engineering. And all of these can be staged in a way that enable multidisciplinary analysis and optimization. The availability of the model-based definition will return dividends just within the realm of design and engineering. Factor in the data needs of other operations that are performed throughout the entire life cycle, and the importance of technical data is immense. It also needs to be a two-way street. The consumer of a product may have a legitimate need for 3D model-based definition, definitely for form, fit, and function, and operations, maintenance, installation, and training, as mentioned earlier. But there are other circumstances where a much deeper level of sophistication of product data is necessary at the operational level. Technologies such as digital twin, mixed realities, condition-based maintenance require information that a few years ago would have been considered protected intellectual property. The time is not too distant when the delivery of the 3D model-based definition with associated non-graphical attributes will be as commonplace as firmware in electromechanical devices. The other side of the two-way street is the transfer of the model-based definition to a manufacturer. The predominant method of providing specifications to have a part built is through the use of engineering drawings. Recent experience, supported by a series of DLA pilot projects, has shown that providing product data in lieu of engineering drawings results in reducing the time to deliver the part, reducing the amount of explanatory communication between the parties, and although something we will never want to admit, reduce the potential errors in transcribing the model to a drawing and back to the model. But what does this have to do with policy? In the same way we will expect our suppliers to provide model-based technical data, we must be prepared to provide the same on the front end. In the way we want to assert and protect our rights in technical data, we must be prepared to accept and protect their intellectual property. In the way we want to keep the cost of acquisition of technical data low, we must recognize that technical data has become a tangible asset, requires a significant investment to develop, and can contain information actually worth protecting. There have been several attempts over the years to issue technical data policy at many levels, but usually they address the acquisition of the technical data superficially and do not address the enterprise at all. In recent years, the Department of Defense has taken an interest in digital engineering. really as an extension to the model-based systems engineering. A holistic systems engineering approach may be appropriate for technical data policy. Technical data needs to be considered within the context of an overall model-based environment that can be scaled and applied at the department level, service level, and component level, while simultaneously enabling deployment and enforcement at the user level. What this means is the policy must provide appropriate guidance to develop instructions that can be harmonized to the maximum extent while allowing flexibility to meet specific business needs. These instructions will then be implemented through the development of user guidelines and processes that enable applications to satisfy the vision and mission provided in the policy. Technical data acquisition is one of several issues that need to be addressed. A great deal of thought and discussion has been expended by the Mantech Advanced Manufacturing Enterprise subpanel. We have been talking a lot about the model-based definition, but if we are going to institute the policy that will provide the right data to the right place at the right time for the right cost, we need to ensure the availability of a model-based environment. Let's take a look. Under DigitalThread, we find model-based definition. At first glance, model-based definition looks insignificant. It is but one of the top 20 concerns of the MBE. But the picture is misleading because the model-based environment relies on the existence of a well-managed set of digital technical data, and without the model-based definition, there is no digital thread. The point of this is the MBE is predicated upon four major thrust areas. These thrust areas implicitly link the technical requirements while supporting a business case for the model-based environment that will support model-based engineering across the model-based enterprise. These thrust areas can be used to identify the key elements of the framework for the model-based environment policy. These thrust areas were used to identify 5 major components that an MBE policy needs to embody. These are infrastructure, which should take a standards-based open systems approach to enable the digital thread in a cybersecure environment that will protect intellectual property. The model-based definition, which we have declared ad nauseum to be the reason why this is all necessary. Digital engineering technologies, which are the applications that power digital engineering. The workforce, which consists of current and next generation that will need initial and recurring training. And finally, fostering an environment that will enable collaboration both within and across enterprise boundaries. Which leads us to this. The scope for a technical data policy in a digital thread-enabled, model-based enterprise. It has everything to do with new business practices relying on the use of these digital engineering methodologies. It has everything to do with the business practices that will leverage the applications to provide cost savings and to reduce cycle times. The policy needs to be in line with the DoD digital engineering strategy. The policy needs to be rigid enough that it sends a signal in no uncertain terms that the acquisition, the creation, and the maintenance of the model-based definition within a model-based enterprise is a priority, and it's a priority that will be enforced. Yet it needs to have the flexibility in order to incorporate emerging technologies and to support the agility necessary to enable the end users to adapt to meet an unanticipated need. We have taken a look at several issues surrounding the model-based enterprise, discovered that there are a lot of E's in MBE. No matter how hard we try, we just cannot seem to escape the pull of the drawing. That from our perspective, it's all about the model-based definition. In increasing numbers, the operation and maintenance of a product is depending on technical data that a few short years ago may have been considered protected intellectual property. These are issues that every enterprise will be struggling with. Today, the government is primarily a consumer of data, but as industry continues to increase the use of tools and processes that depend on a 3D model-based definition, the government will also become an author. That the emerging technical workforce is already showing signs of being 100% data-centric. We need the policy, guidelines, and infrastructure necessary not just to be a participant, but to be a leader. I think that we have the resources at LMI to help with the preparation, especially in some of the special cases that apply within the Department of Defense. Please feel free to contact me to discuss any of these issues related to the digital thread-enabled model-based environment. And don't forget to join DeadMig. Don't cost nothing. Let's all be good so we can see each other face to face in Golden this winter.